I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on capacitors. In this video, we're going to have an introduction to capacitors. So, what is a capacitor? So, a capacitor is two parallel plates that are in close proximity, so we'll call that distance d, and each of the plates has the same area, we'll call that area A. Now, if we hook up those parallel plates to a source of electric potential or voltage, what happens is that electrons move through the battery off of the positive plate and then onto the negative plate, leaving us with two charged parallel plates, as we've seen before in our electric fields. The charge stops being transferred when the potential difference across the plates is equal to the potential difference across the battery. And then the capacitor stores electrical energy through that electric field. Now, to calculate the capacitance of a capacitor, what we know is if we remove the battery and we just have those charge plates, the capacitor is a ratio of the charge of the positive plate to the magnitude of the potential difference between the plates. So capacitance is equal to the charge divided by the potential difference across those plates. So capacitance can be calculated by just taking Q of the positive plate divided by the potential difference across them, where C is the capacitance measured in farads, which is a fixed value. Q is the value of the charge of the positive plate, and delta V is the potential difference that's measured across the plates, and that's measured in volts. Now, looking at capacitance a little bit further, if we define this value sigma as the charge density or charge per unit area, coulomb per meter squared, that just means how much charge we have in coulombs for every square meter of area. So if we look at that a little bit further, we can calculate the charge by multiplying the charge density by the area, which the meter squared would cancel out, leaving us with coulombs. So that's a way to calculate the value of the charge on the plates. And delta V, the potential difference, is the electric field times the distance. Now remember, that's for a constant electric field, which would be a constant electric field being measured across those parallel plates, as we've seen in the previous electric fields videos. Now, the electric field can be defined as the charge density divided by epsilon naught, which is known as Gauss's law. It's not something that's discussed much in physics 2, but we're going to substitute that in for our electric field. And we can see that we have a charge density in the top and the charge density in the denominator. So we can simplify that by canceling them out, multiplying by the reciprocal of epsilon naught, and that gives us an equation for capacitance of epsilon naught times area divided by the distance between those plates. So we can see that only the geometry of a capacitor affects the capacitance, as epsilon naught is a constant and the area and distance are the only things that impact the value of the capacitance. So this is why Q and delta V don't impact the capacitance. So we can calculate the capacitance of epsilon naught times A divided by the distance, but this is when we have air in between the two parallel plates. So we can drop a dielectric in between the parallel plates, and this would impact the value of the capacitance with that constant of the insulating material between them. And the C is the capacitance in farads, where A is the area of the plates in meters squared, D is the distance between the plates in meters. The epsilon naught is the vacuum permittivity constant, and kappa is the dielectric constant of the insulating material between the plates. And those values for the dielectrics are greater than or equal to 1. So this is going to increase the capacitance if we have something that has a value greater than 1. But for most of what we're going to be calculating, the value of the dielectric is going to be air, which is equal to 1. So that means we'll just be looking at the epsilon naught times A over D. Now let's talk about the electric field in a capacitor. So when we hook the battery up and that potential is creating that charge to move from the positive plate to the negative, we now have the positive charge plate closer to us. We note that the electric field lines point from the positive to the negative. And we know that the electric field in a parallel plate is going to be constant. We know our two equations for capacitance, that charge divided by change of potential, and we can set those to equal to kappa epsilon naught A over D, and we can substitute that delta V is the electric field times the distance. And now we can see that we have the distance on each side of the equation in the denominator, so we can cancel that out. Then we can rearrange and solve for our electric field, where we get E is equal to Q divided by kappa epsilon naught times the area. And this is how you can calculate the electric field in a parallel plate capacitor. So now we're going to talk about the energy that's stored in a capacitor. So again, when we hook up the battery and we move that positive charge, now the positive charge is in the back. And we know that capacitance is a constant and only affected by its geometry. So the area and distance are the only thing that are going to impact the capacitance. But if we increase that potential, we can see that there's much more charge that is moved. The charge density increases when we've increased the potential. Remember, the charge continues to move until the potential difference is equal across those plates. And then Q is going to be a much larger value on each of the plates. Remember, Q is the value on the positive plate. So that tells us that Q is directly proportional to the electric potential. And if we know that those are directly proportional, we can make a graph of Q divided by delta V, which, if they're directly proportional, it's going to give us a straight line graph. If there's no charge, there's no potential, then that means there's no charge. So looking at our capacitance equation, we know that the slope value is going to be the value of the capacitance. Now, using graphs to find slopes, we can also use the graph to find the area. So the area underneath the curve is going to be a triangle. That triangle is going to be 1/2 the height times the base, which is 1/2 Q times delta V. And we can figure out what the area underneath that curve is by looking at the units. So 1/2 Q times delta V, we can look at the units for Q, and we know that the units for Q, that's the coulomb as the measurement of charge, and delta V is a volt. But we also know that a volt is a joule per coulomb. So canceling out coulombs, that leaves us with a unit for joules. And joules is a unit of energy, which is the potential energy that is stored in the capacitor. So to calculate the energy in the capacitor, we just need to know the charge on the positive plate and the potential difference measured across those plates to find the potential energy stored. Now we also know that C is equal to Q divided by delta V. So rearranging that equation, Q is equal to delta V times C. We can substitute that in for charge in our electric potential energy equation and simplify it and give us another equation of 1/2 the capacitance times the potential difference squared. So we don't even need to know the value of the positive charge across the plate. So UC is the energy stored in the capacitor, that's measured in joules. Q we know is the charge of the positive plate, measured in coulombs. Delta V in both equations is the electric potential across the plates, and C is the capacitance of the capacitor, and that's measured in farads. So let's recap the capacitor equation. So capacitance remember, is the ratio of the positive charge plate to delta V, so that's C is equal to Q divided by delta V. And the capacitance is only based on the geometry and the dielectric constant, where C is equal to kappa epsilon naught times A divided by D, where most times kappa, our dielectric constant, is going to be 1. Now the electric field between the plates can be calculated as the charge on the positive plate divided by the dielectric constant times epsilon naught times the area of the plates. And then we can calculate the energy stored in a capacitor, that potential energy, with these two equations, 1/2 Q delta V or 1/2 C delta V squared. And that's the way we can calculate the energy stored in our capacitor. So why do we use capacitors? Well, what a capacitor does is it is used to store large amounts of charge. And that causes energy to be stored based on the amount of charge and the geometry of the capacitor. And then the charge or energy are delivered quickly for a one-time use for a device. The capacitor then charges again and repeats the process. So capacitor is effective. And here's some common uses of capacitors. Tuning a radio. When you tune a radio, it changes the capacitance, which then allows it to pick up different frequencies. Another use is, you probably use this, is delay windshield wipers. So the delay windshield wipers charges the capacitor, and then the capacitor discharges, and then the windshield wipers go ahead and clean the windshield. Another use is in some keyboards, the capacitors are what are used to allow the letters to be typed. So when you press a letter, it tells the computer which letter is pressed by the discharging of that capacitor. And also camera flashes. So in your phone, when you take a picture, a capacitor charges very slowly, then it discharges very quickly to give you that flash to take your pictures. So this is an introduction to capacitors. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.